Mic check, mic check. I'm gonna warm up the stream for another minute or so. Sorry, running a tad late. Oh man, the music stopped. Why didn't it keep playing? There it goes. Got my cat on stream. All right, we're ready to start. Except for my cat. Yeah, I'm gonna have to. All right, let's kick out the cat. All right, let's go ahead and get started. So I wanted to go over the homework today, but I'm also just taking any other questions that you have, anything in the chapter that is ambiguous or anything. So let's start with a couple of these examples. So write the IUPAC name for each of the following structures. Let's see, let's do the first one. So we have an alcohol group here. So this would be, we have meth for one methyl group. So this is methanol. Let's see. What about, try this one for a second. Give everyone some time. And so you should recognize this is an ether from that oxygen in the middle. And then so let's look at our two sides. So we have an ethyl group and a propyl group. So I would call this ethyl propyl ether. Well, let's look at this one because this is, what's the little, it's a little subtle difference because we have 1, 2, 3 carbons there. But notice the connectivity. So if you were to draw this out, O, CH3, and then so this is connected to a carbon there, H, and now this is connected to 2 carbons, right, 2 methyls there. And so this is an isopropyl group. So if we wanted to name it, we can name it isopropyl, and then methyl, methyl ether. Okay, let's look at another one. Let's try this one right here. Give everyone a couple of minutes, a minute or so. And so let's start by just drawing this out. So we have our CH3, CH, OH, CH, and look, there's our isopropyl group again. And so let's try to identify our longest chain. So we have 1, 2, 3, 4. That would give highest priority to the OH group. So let's do that. So 1, 2, 3. It wouldn't matter. This was 4. This was 4. And so this is butyl or butane, butanol. So 3 methyl, 2 butanol. So let's try to do this next one. So draw a structure and write the formula. And so the thing that I've been seeing is kind of the isomers has been giving people some issues. So remember, isomers have to have the same formula. And so we'll look at different types of isomers. So when we've been looking at these examples, we've been mainly looking at structural isomers, so things that have the same formula but may be constructed a little differently. So we saw that with like the alkanes and exploring things with the same degrees of saturations. So let's do this one. So 2-methoxy butane. So we have a methoxy and butane. So let's just start off with our 4-carbon chain. So 1, 2, 3, 4. And then I can just label this 1, 2, 3, 4. And then 2-methoxybutane. So that's going to be an OCH3 for methoxy. And so let's write the formula. So 1, 2, 3, 4. So C5, H. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then O. So now let's do this one. 2,2-dimethyl 1-propanol. And so propanol, now let's just call this carbon 1. So we have our OH there. And then so 2,2 will look something like this. And so now let's do our formula. 1, 2, 3, 4, 5 carbons. H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. H12. Then we have an O. So 1-ethoxypropane. So let's start off with our propane again. And then, so ethoxy. Put our 1 there. And then our ethyl. So it looks like an ether. Oops, and did I drop a carbon accidentally? So 1, 2, yeah, I did. Just make sure when you draw these, you don't drop any. carbons or anything. So 1, 2, 3, there we go. 1, 2, that looks better. So let's look at our formula. So C, 1, 2, 3, 4, 5. And then H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. O. And then our last one, 3-methyl butanol. Oh, excuse me, 3-methyl 2-butanol. So let's start. I'm going to start with my 1, 2, 3, 4, my butane, so 4. And then it's 2-butanol. And so I'm just labeling this 1, 2, 3, 4. OH is there. Now I need my methyl. So 1, 2, 3. Put my methyl group there. And so let's count up our formula. 1, 2, 3, 4, 5. H1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so now this question asks, are any of the 4 above compounds isomers? And well, we said isomers have to have the same formula. So actually, they're all isomers. They're all isomers of each other. They all have the same formula. They're just different structurally. So now let's go through some of these reactions, and this will be good. So take a minute, and I would probably write this out because I can help you too if you need. So we have our ethanol plus our acidic conditions. So do we remember what happened? So you can kind of remind yourself. So we had this acidic condition. We formed our water because it got protonated. Then we had this other hydrogen that could get attacked by water. So then that would cause it to leave. Those electrons go there. Water leaves. And so that left us I did not draw that correctly. Let me redraw this. We have our OH, carbon, hydrogen there. So our H is there. This is a hydrogen that's going to leave. So that gets attacked by water. Those electrons form there, and then this leaves. There we go. It's a little clearer. And so that leaves us with our double bond, which is what we should expect from this dehydration reaction. And then, of course, plus water, since water left. So now let's try this next one out. So 1, 2, 3, just making sure I have enough carbons. Always make sure you double count your structure. And so here we could make 2, let's see, where is our hydrogen? So going to lose one of these hydrogens, potentially. And so if you notice, right, this would give us a symmetric product. So we could go either side. Just want to draw this a little bit better. I don't like the way I drew this. Okay, I think that's a little clearer. And so again, we have our same sort of mechanism. So our OH is going to be protonated from our acidic conditions. And so now we have to lose a hydrogen. Again, it doesn't matter which side, since the product will be the same. And so your product should look something like this. So we could have lost our H from here, lost water on this side, lose it from here. Again, symmetric by rotation. So what happens to butanol under oxidizing conditions? Let's just write butanol. 1, 2, 3, 4. And our OH. And so if you remember, these get oxidized. Oops. That's obnoxious. I put it in the wrong spot. Sorry, I was just trying to flip over. So for oxidation, remember that we could take it to the aldehyde if we're just doing our one step here. And so let's go back to our paper. There we go. Managed to find out my printout. And so our product would be 1, 2, 3. So my product would be 1, 2, 3, 4. So 1, 2, 3, 4. And then our product there. So now let's try 2-butanol. So 2-butanol. I'll just draw 1, 2, 3, 4. Our OH there. And so now it's not terminal. So what's our product? So let's draw it 1, 2, 3, 1, 2, 3, 4 again, and then just make the ketone there. And so now these are just, can you come up with a derivative? Do you know what a tertiary alcohol is? So tertiary alcohol has to be attached to a carbon with 3 separate R groups. So something like this. They could all be methyls. I just put R1, R2, R3 for simplification. So what about a secondary thiol? What does that mean? So we know a thiol is SH. And so if it's secondary, right, it's attached to, the carbon's attached to 1 hydrogen. And then we can have 2 different R groups. So most of these are pretty straightforward, but I do want to go over this one. So this one has a funny bridge head. And so I just wanted to point this out, that this is kind of 3D here. So you have this nitrogen is kind of going up, right? And then now we have a bridge carbon. So we have like a two carbon bridge over here. So there's 1 carbon, 2 carbon, and then it reconnects back down. So we have some sort of 3D geometry. I just want to show you another example. So this is just adamantane as an example, but I just wanted to point out, you know, again, that 3D kind of bridgehead structure there. And so this is what this structure looks like in 3D. That can kind of help you with imagining this molecule in 3D. And unfortunately, I don't know what it is, or else I would try to look it up. And so let's see if we can do the molecular formula for this one. So let's count our carbons. Ready? 1. I'll dot them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So C21. Now let's do our H's. This could be a pain. So 1, 2, 3, and then 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So H23. And then let's see, nitrogen. The rest are in alphabetical order. So nitrogen, we have 1 nitrogen. And then let's count up our oxygens. So 1, 2, 3, 4, 5 oxygens. Any questions about anything so far? A lot of this is fairly straightforward. Let's do, this is another just fun one. Let's do this one. Let's draw the structure of 2,4-dinitrophenol. And then is it primary, secondary, tertiary, or aromatic? So now let's draw. So our phenol ring has our OH on it. So this is 1. And then if it's 2, 4, so 1, 2, 3, 4, 5, 6. So 2 is our first nitro. So 1, 2, 3, 4. Here's our second nitro. And of course, this compound would be aromatic. And so nitro compounds are pretty toxic, just FYI. They're usually like highly colored. They're pretty interesting, pretty relevant for synthesis. Are there any questions or anything? I wanted to show you this nitrophenol, since all the phenols tend to have some cool colors in them. And so this one's pretty cool. You know, this nice bright yellow powder. That just has to do with its conjugation. Just trying to see if it would link to other nitrophenols by any chance. Just so we can look at more pretty pictures. Here's another similar one. Oh, it doesn't have a picture. And so the other thing is, and this is kind of interesting because I think I mentioned that they're toxic. And so looking at the Wikipedia of this, it can be used as a pesticide. So that's kind of interesting. Oh, apparently they're trying to look at it for treating obesity. That seems interesting, but they mentioned that it's too dangerous. It's kind of funny. I think it's funny. But yeah, so these are toxic. Wow, this is actually fairly toxic. So don't eat your phenols. That's my safety tip. So here are just other ones. I just wanted to point them out. So, for example, 4-nitrophenol. Just another one. Also, you know, very bright yellow powder. So these are all pretty colorful. Trying to look for other examples. Well, this is a good one. So CH3, COH, oxidize. What would our product be? And so I would draw this out. But then our question is, this is, sorry, CH33. So what's the problem with this? And so kind of the problem is there's no hydrogen. So we can do any sort of elimination. And so even under these oxidizing conditions, would have no reaction with that tertiary alcohol. And then let's look at this one last thing because I don't think we covered it. So now it tells us to compare the OH group and KOH, methanol, and phenol here. And it says classify the OH as acid, basic, or neutral. And so let's go through these. So we know KOH, this is basic, since it makes hydroxide ions in solution. Now this one, does ethanol dissociate in solution or anything? So this one is neutral. There's also no resonance structures that we can do. But phenol is a little bit different. So if we were to deprotonate this can be stabilized across this entire ring. And so this proton is going to be acidic. And so you can tell it's acidic because basically you test it, you take off that hydrogen, and then you kind of ask yourself, like, is this stable? Is this not stable? And so again, in this case, you have your aromatic ring to stabilize it. So the last thing I want to go over is our boiling points. So we have to rank them. So we have butane. Oops. Pentane. Butane. 1 propanol. Ethyl methyl ether. And then our last one, ethane thiol. Oops. So now we're trying to order these. And so we could find their molecular weights. We could also, they're pretty similar in molecular weights. But let's see if we can order them. So who would have the lowest boiling point? And we want to judge this by their intermolecular forces. So butane only has London dispersion, otherwise called those van der Waals forces. Propanol, though, has, of course, London dispersion. It has a dipole moment. We got OH on the end here, so dipole-dipole. But then we also have hydrogen bonding. And so that's pretty strong. So if I just basing it off of these bonds right now. So this is the lowest. This is probably the highest. Then we got our ether. So our ether is still polar, kind of somewhere in the middle. And it's going to have dipole-dipole. And of course also the London dispersion. And then this last one, excuse me, would also have dipole-dipole and London dispersion. And so now this is kind of tricky because we're trying to pick between ethane thiol and ethyl methyl ether. So now let's look at their molecular weights. So ethyl methyl ether, let's just look it up. As long as you promise me you know how to solve these, right? We just add up all the components. Usually chemists just look up, oh my goodness. Yes, this is what I want. And so its mass of ethyl methyl ether, just making sure it's the right one, is 60. Grams per mole. Let's try to check that ethane thiol. And so its mass is 62. So again, this is a pretty hard call between these two. So now I'm trying to look at some other things to help us. Just trying to find its dipole moment, just to see if it had it to compare. Because this is a little tricky. Kind of annoying. So now we're kind of debating between these two. The thing is, so our oxygen is also more electronegative, so they're pretty close in molecular weight, so that doesn't help us too much. And so let's just start ordering them. So butane is going to be the lowest, so that's nonpolar. Then we're trying to compare ether versus thiol still. And since oxygen is just more electronegative, this seems to be the more polar one. And so next should be ethane thiol. And again, this kind of would have been a hard judgment. So if you could justify it and say that their molecular weights are pretty similar and you would swap them, I probably wouldn't mark you wrong. It's just that the polarity on ethyl methyl ether is greater. And ideally, let me see if I could find. Because what we really want to compare is the dipole moment. And, we're trying to make these judgments off of the dipole moment, just based off of our visualization. But you could also, determine this experimentally or with computational chemistry. And that's kind of useful. And so here's what I'm looking at. So I'm just looking at this dipole moment here, just how susceptible it is to polarization. And I'm not quite satisfied with our answer. That's why I'm looking, so that we all really feel like we're on the same page. Because I understand that it's hard to judge. Sometimes it's nice to have more quantitative data. I wonder if this has other compounds. Just trying to find. So if you could find a nice, there we go. I was just trying to find it from the same source. So this is good. And so NIST is always a good website for looking up standards. So National Institute of Standards and Technology. And do we have a dipole moment here? Oh. I'm not sure that they've calculated the dipole moment. That's kind of... Oh, there we go. Dipole. Okay. So here, this may not even be that much more helpful. Now I lost the dipole moment for this one. So ironically, this methoxyethane compound seems to have a lower dipole moment, which is not what I was expecting, because it has a higher boiling point. Now they're pretty close. So again, that's why I think it's a pretty tough call. Welcome in the chat. Let me know if you have other questions or anything. I'd be happy to answer. And so looking it up, the boiling point for ether is 45. Oh, let's put our propanol. So we know, and this one, the ends were kind of easy. But in my opinion, these were kind of difficult. So this was 45 degrees Celsius versus 35 degrees Celsius. And so there may just be probably just stronger intermolecular forces. And then butane, sorry, for completion is -1 degree Celsius. So that is a little bit lower. And then propanol is 97 degrees Celsius. So you can see, right, those extremes were really easy for us to predict. And then kind of the middle gets difficult. All right, I feel like we've covered everything since our reaction of sulfides are just oxidizing. So let's go over the one reaction just so we can say, yes, we know how to do it. And so we have this methane thiol with oxidation. We know that we would form a disulfide bond. Oops, dropped my sulfur there. So just like this. And then, of course, we could do the opposite. So we could start with this product here and then undergo reducing conditions. And then, of course, we would reform that sulfide and, of course, make 2 equivalents of that. All right, I think we've covered everything. And so again, just let me know if you have questions. I'm more than happy to meet individually with people. And then I'm working to get the lab materials up. So I have the lab posted, and then I'll add some videos as we film those today. So it should be a fun lab. We're doing a titration with iodine. And we're using a starch indicator to make kind of that blue complex starch solution. And we'll see how much vitamin C are in various samples. So it should be fun. So I look forward to lab. So I'll hang around on stream for a little bit. Otherwise, have an awesome day.